We'll wait here for some time for others to join.
In the meanwhile, can I ask some questions?
Yeah, sure.
So like in one of those lecture, in one of the lectures, professor said like that weight adding noise to initial input is equivalent to applying regularization with sum of square laws, right? Sum of square error laws.
Sorry, could you just repeat? Like I just lost the voice for some
Okay,
time.
so the professor said like when you add Gaussian noise to input of a neural network, it is equivalent to adding regularization to sum of square laws.
Yeah.
Yeah, so like is sum of square like how much work does the sum of square doing here? Like would why is the like this particular loss function would give like regularization but not other loss function?
Yeah. Let me take that. So I'll just open my notebook. We can discuss it there. Just give me a second. I'm just sharing my, opening my notebook. Then we can discuss there. And listen. Okay. So is my screen visible?
Yeah, screen is visible.
Okay. Great. Uh, so so question was like why like adding Gaussian noise to the weights of the neural network is same as adding regularization to the L2 loss, right?
No, no. The question is why is the sum of square laws special for this thing? Why would others laws such as cross entropy laws or mean square error laws won't work for this?
I mean, so you're saying that why we're not doing regularization for other losses as well, right?
No, I'm saying like why is adding Gaussian noise is not equivalent to L2 weight decay with losses other than sum of square laws.
The sum of square loss is same as I guess MSE, right? I mean, the mean square error.
Okay, yeah, sorry. What about cross entropy laws and other log laws?
The cross entropy loss and the negative log likelihood loss is also sort of like similar, but you can say, yeah, I mean, the MSE and this cross entropy loss are different laws. So the question was why we are sort of regularizing this sum of square loss and not the cross entropy loss, right? I mean,
Like why would this not work for cost entropy loss? Why is this like mean square loss or sum of square loss special in this particular case?
okay, so actually the thing is that so I'm not sure like which particular so actually I didn't go through the entire lecture bit by bit. So I just have an idea of the thing. So what I'll do is that so I'll just tell why we sort of add noise, Gaussian noise to that or add regularization in that loss function because we just need to avoid overfitting, right? So one way is that we can either add Gaussian noise to that or we can do regularization, but we do not do regularization. So we do regularization in the MSc laws, right? Uh, uh, we do not do regularization. Uh, Hello.
Hello, I can hear
Yeah.
you.
Yeah. Yeah. So we sort of do regularization in the MSc laws, and we do not do the regularization in the cross entropy laws. And so it's because like this the regularization technique is commonly applied to the loss function like mean square loss or regression task, but it is very less common to directly apply it to the regularization to the cross entropy loss, especially in the classification task. So one of the reason can be like this. So there's something called inherent regularization. Uh, I mean, so what happens is that in the case of cross entropy, it has already some inherent regularization built into it. So it sort of penalizes the large errors become significantly due to the logarithmic mean that we're using in that. So that so in that in a way that will prevent the model from becoming too confident about incorrect predictions. So this effect is more pronounced when the predicted probabilities are far from the true classes and the levels. So that's why it has a inbuilt regularization term. So that's why we do not use commonly regularization in terms of this cross entropy or NLL, the one you said, the negative log likelihood loss. But if you see losses such as MSC, then it doesn't have any regularization built into it. That's why we have to use the regularization term explicitly. And this answer to your question why we're sort of using regularization in with MSc laws and not with the NL laws. And if your question is what is the connection between adding the regularization term to the laws and what is the uh, loss and adding Gaussian as the weight. The relationship is that there is no direct relationship, but you can say that adding noise to the Gaussian noise to the weight also sort of prevent the weight, uh, so prevent sort of the network to learn similar weights. It sort of makes it harder for them to learn similar weights. So the network will try to learn under the constraint that there is some random noise that is getting added to the weight, and this sort of making the network more regularized or more constant. And when we add a regularization term to the loss function, we say that no, we don't want those weights which are very high or very low. We want the weights in a certain region. We want the weight to follow certain properties. Given that this property is followed, give me all those optimal weights. So when you do this sort of constraint on top of the weights, we get better weights, and the network sort of get a chance to explore all the possible weights and give us drivers and more generic weights that represent the dataset more clearly, and not something that will memorize the entire dataset. Does that answer the question? Like, I'm not sure.
Yeah. Can you give me more resources regarding how cross entropy loss and negative log likelihood loss is self-regularizing? I
Uh,
have difficult grasping that.
Okay, so I'll give you in some. I'll look through it and see like where exactly I can find the like a good explanation and thing. So if you could raise a question in the this discussion forum, I'll try to answer that with the link.
Yeah, okay. I will. Um,
Okay,
um,
sure.
okay.
Uh, okay, I guess there's. I'm not sure like why people are not joining. There are like two, three
Actually,
sessions
there
going.
were few people joining and they left.
Joined earlier.
Yeah, if the participation count increased to like four at one point, but then it decreased again.
Okay, I joined at 10:31, I guess, but I'm not sure. Like, I mean, I thought like 2, 3 minutes is fine, but yeah, I guess I'll
Yeah,
try to join.
actually, your session goes parallel to another session of the same course.
Yeah, 3 sessions or 2 sessions. I'm not sure. Yeah, so I'll
Yeah,
try to
so like
reschedule it. Yeah,
yeah,
and
so like it
yeah,
would be better for everyone if yeah, you guys can like separate your time zones out because this does not help anyone.
yeah, yeah, exactly. So I'll ask the NPTEL people to do that. So last week no one joined, and it was August 15th. And see, my friend got like 5 or 6 people or 10, maybe. So I thought I don't have to do the live session, but I wait for like half an hour. But then these guys told me that even if there is no one, you just have to open up the PPT and like talk like even if no one is listening, you just have to present and wait for them to like come or see the video later. But I don't think no one will watch the video later. But yeah, is there a
Yeah,
criteria
like
that
it's
I have?
because of the time conflict. If you can sort this out,
Yeah,
everyone would be benefited.
I'm currently in Australia, so now the time is like 10:11 p.m. here. So also this sort of timing is very difficult for me to adjust because it will end here in like 12:30 or 1 in Australian time. And Australians
Um,
like just go to bed in 9 p.m. and they wake up at 5 a.m. So it's very hard to cope up with that because everyone wants you in the lab by 8:30 or 9 a.m. in the morning. So it's very
yeah,
hard to
would it
like
be possible to do a morning session then?
yeah, it I would love to take a morning session, but I don't think they have any slots for that. So I'll write a mail to them that give me some time which I am comfortable and also it aligns with the NPTEL guideline or this guideline. But I think the reason they're starting from 6 because they assume that there are some working professionals also taking these live sessions and they will be free after 6. Technically should be free by 5, but yeah, 1 hour for commuting or getting the stuff right. So I guess that's why they are putting it on starting from 6, and on weekends they start from 4. But on weekends, I'm not sure. Like people here in weekends, they don't work; they just roam around and make noises. So I don't think it will be a healthy environment to teach on weekend. People will be shouting. So I thought like I'll just stick to that, even if I'm sleeping at. I mean, if I'm staying awake and doing nothing, it's fine. But if I'm teaching till 1 a.m., it's uh, kind of yeah. Okay, so if you wanna stay, you can stay. So what I'll do is I'll just go through. So we prepared a slide. So I'll just go through that slide and explain things that is there in the slide. Like that will be like covering the short topics about it.
Like if you like it would be I think more helpful if you could cover like questions, like for example previous year's question or like questions similar those things, or even like programming assignment like type of questions, sample questions, rather than like going through like the lecture, because like we have already seen the lectures, right?
Yeah,
Like it
I
would
mean
more
the
helpful, like this is
what
like
happens
supposed to
is
be
that
problem solving session.
yeah. What happens is that people don't see the lectures properly. So what we do is so what we have decided is that so the faculty he Vineeth we got into a call and we discussed that I mean these two of the guys were doing this TSA last year as well. So they say that what they usually do is that they pick a topic from the lecture and they discuss that for like 1 hour or 40 minutes or 45 minutes, like just 12 slides, I guess. Yeah, 12, 14 slides. So they do that. And once that topic is done, they do the programming exercise. I'm not sure I have access to the programming exercise yet or not. Let me check. Get. But yeah, so we can do that. We can do the programming assignment, given that I think this course people are seriously taking and sort of watching the lectures. But the previous course that I was tutoring, people did not know much, so I just had to go through the lectures and revise the lecture content once again. Let me go to the programming part. So, do they share any GitHub link of all the notebooks that they have for the course or something like that?
I'm not aware if it does exist.
Okay,
Like it is not available in the normal course outline session. Like we are only given access to notebooks after the week passes. Like you know, so
okay, I
once the
see.
week passes, we get access to that week's notebook, and so on.
So you have notebooks for week 4 as well.
Yeah. So, but only no the week. Yeah, week four only week four. We don't have access to week four and further notebooks.
Okay, let me open the notebooks. Hmm, okay.
Uh, did you get it or?
Yeah, I'm just 1 second.
Okay.
I think they shared a mail. Uh, I cannot find it. See that. So, yeah, I find it. Week 4, right? Yep, they have notebooks like this. I hope it opens in the collaboratory. Yep. So do you have yeah? So you can discuss the code, but uh, Yeah, so I'll skip this part where we'll discuss we're able to discuss about perceptron and this how this linear separation works, multi-layer perceptron, activation function, and all these things. But so if you have any doubts in this part, we can discuss that, or we can just go to the code directly.
I would prefer if you go to the code directly because like the lectures already exist, no, and it's not like I have any issues with them. So I'd be grateful if you can go through the code because there's no equivalent, like the lecture equivalent of the code, right? Like this is it then.
Yeah. I mean, no. So we have a code for each lectures, I guess. Just given.
We do? We do?
Yeah, I mean, it's not like no, it will align with the lecture, but it has some some sort of correspondence.
Can you point me because I couldn't find it?
I think uh yeah, so just see can you access this or not. Can you access that?
Um, uh, it's a Jupyter file, right?
Yeah,
Yeah. Um,
so like if you go before that, like if you go to the prior section here, like you can see there is notebooks for each week that correspond to lecture 1, lecture 2, lecture 3, up to lecture 10 in week 4.
okay. These is not linked. This is not linked actually to our course outline.
Yeah, maybe like I think they just put it outside, and I'm not sure why they haven't linked. This would be okay. So I'll be discussing this code, and I'll discuss the content later because yeah. So actually, I am recording this. I have to put it somewhere. So I'll just start discussing things, and if you have any questions, you can pause me. Then we can discuss about that. So starting with the imports here, like yeah. So I hope you're comfortable with all these libraries. If
Yeah,
you
you
have,
can skip the imports.
yeah. So and they are like NumPy library, which is used for like matrix computation. There this is the Pandas library, which is used for reading the CSVs, and is the matplotlib library that is used for plotting the codes and all. Then coming to the PyTorch libraries, which are like the first one is the Torch. So Torch is a PyTorch library that facilitates us to write good and simple neural network code. And Torch Vision is a PyTorch library that is specifically designed for computer vision, and it is specifically designed to host models and data sets that is there in the computer vision domain. So we'll run that. Let me set up my GPUs as well. Yeah. Just change the runtime type to okay. So are you familiar with creating tensors?
Yeah,
I mean,
I'm
you
familiar with
must be.
Tensor.
Yeah. So like tensor, we can create the tensor from a list, and we can create the tensor from matrix and tuple and sets, and we can also create tensor of ones and zeros like this. The idea behind tensor is that tensor is a multidimensional vector, and so a general term for any n-dimensional real number set is called tensor, and tensor, we call tensor to for example, like vector is a 1D tensor and matrix is a 2D tensor and an image is a 3D tensor. And creating tensors in PyTorch and sort of playing around with it and creating the neural network on top of it is important because there are two major things that PyTorch provides. One is the autograd, or which you can say the automatic differentiation that the auto diff, which is facilitated by the PyTorch. It's sort of whenever we do any computation using any variable that we have declared, so it will keep a track of all the gradients or and all the things that is going through that variable, so that later if you want to backpropagate, or if you want to calculate the grad of a variable across with respect to some other thing, we can do that. So it sort of maintains all those gradients in it. So that's the beauty of tensor. And second thing is that it can work well with GPUs, so that we can do many heavy computation parallelly. So this is all about creating tensors. You can run this plug and see how it has created the tensor out of this list. So it was earlier a list object, now it is an object of a tensor. And so this block is all about like common tensors that we have. Like one is like the ones tensor, where the tensor block will be it will create a block of 5x3 tensor with just ones, and similarly for 0 and similarly for empty.
Yeah, okay.
So so then coming to the distribution. Yeah. So when we're when we say we're generating random numbers, those are actually not random. So what we do is that we sort of sample from a probability distribution. So this first line, when we say rand dot rand, it sort of uh, uh, samples from an uniform distribution, and when we say rand n, it sort of samples from the normal distribution. So these are the two way like to create random tensors in the library. So you can see this is the random tensor that is coming from this uniform distribution, and the second is the coming from normal distribution. Okay, so reproducibility. Uh, so uh, so Python has this random number generator, this the randn and random. But so when we are working with a neural network, and when we're sort of trying to with different metrics or different settings or different input to that, we don't want the input to the we don't want the weight to change. So that's why if we set torch.manual seed, it will it will uh, it will seed the random number generator in all the devices, that is including CPU and GPU. So the manual seed will, I mean, all the random number that will be generated after running this code will be same for every time that you run. That's why you can perform your experiment uh, assuming that all of the weights are starting from the same point. Okay, so I guess this is the text block only. You don't need to run anything. We define for a wave function called set series that does it. Okay, so here it's sort of this function is sort of setting the seed so that you get the same random numbers every time. So why do we need random numbers every time? I just discussed that why we need, because when we are trying to evaluate a model against so many different training paradigms or something, but we want the training process to start from the same point. So that we'll be able to compare them and evaluate them according to our need. So I'll run this block. Okay, so here is a code like to see if this rand and rand n that they're getting is all same or not. So okay, so the same. Okay, so yeah, I mean, uh, 0.49.
Yeah, you can continue.
Yeah, yeah. I mean it. Yeah, I mean if you just run it multiple times, you can see every time you run, it should be different, but it is coming same. It is 0.49, 0.76, 0.08. Yeah. When you set this set to false, you can see different output. It's 0.03, 0.18, and it's 0.83, 0.20, and run it again, 0.94, 0.88. So the beauty of this is that when you set the seed as true, it will always generate something that is same for every time. So yeah. NumPy like number ranges. Okay, so it's just the like if you just want to arrange 0 to 10, it will give you a list of item from 0 to 10, including excluding 10, and the similar function is numpy arrange, and linspace is same as linspace. So I don't think much need to be explained here. So yeah, operations is PyTorch. Yeah, so it's better to like so torch has this functions that is torch.add, torch.multiply, but so tensor has all these things like add, multiply. So what they've done is that in the class of tensors, they must have overloaded the tensor uh, operations of some difference multiplication with that. Along with that, they also have this add function along with it. So yeah, so just adding and multiplication. You can check that out later. Operators are yeah. So the thing I said, in PyTorch, most common Python operation are overridden. That means like if uh, the plus sign is there for common two normal number to be added, now it is overridden to work for tensors. So you can do any sort of operation that you are doing with any numbers or vectors with tensors. Uh, NumPy equivalents, yeah. So tensor methods is like same. Like if you say sum will just add all the tensors. If you say sum across an axis, so axis is like axis equal to 0 means across the columns, axis equal to 1 means across the rows. So you'll there's a sum all the tensors across rows, across columns, and same with mean as well. Then coming to the matrix operation, uh, uh, yeah, so this at the rate symbol is used for matrix multiplication. And is there any other? Yeah, so you can also use this matmul function. I didn't know that like at the rate is used because I always use this matmul function. And also like for dot wise multiplication, we can use dot. I think this Agility is the new version or something, or is it old when I was learning this? But yeah, uh, yeah. To transpose, you can use .t or .t, capital T. Yeah, that's about it. Like just normal multiplication stuff. And this is the dot product, which is dots dot dot. So it's pretty simple, straightforward. And yeah, then coming to the manipulating tensors in PyTorch. So first is sort of saying indexing. So it is same as the torts list, where if you just print X, it will give you the entire list. If you it also have negative indexing like -1 if you want to work from the backward, and including 1 and excluding 3. So it's just 1, 2, and -2 means starting from 0 and excluding the last two. Let's run this. Then we have multidimensional tensors indexing rules. That is like same as NumPy. Like if you have tensors with more than one dimension, how to access them? So is that flatten and reshape. So if you are familiar with flatten and familiar with reshape, so flatten is something like given a tensor, let's say 2 cross 4, and if you want to flatten it, it will be 2 into 4, that is 8 cross 1. So everything that you need, that you have in the dimension, multiply all them and cross 1, you get the flattened output. So if the shape is 6 cross 2 cross 3, the flattened output will be 12 into 3, that is 36. Yep. And reshape is like reshaping the tensor, and you should keep in mind that like after for reshaping to work, the the reshaped proposed reshaped dimensions multiplication should be equal to the current steps multiplication. Yeah, to check the safe function is there, and yeah, I guess this, yeah, is all safe. Permute. Yeah, so then coming a part that is called permutation. Permutation will let's say like the dimension of tensor is let's say um, 3 cross 18, 3 cross 100 cross 100. So if you want to permute that, what will happen that the resultant image will be like 100 cross 100 cross 3. So you just have to remember that while representing the image or printing the image on the uh, like plotting the image on the Python notebook or even saving them, we cannot plot it with 3 cross height cross width, or 3 that is represented for RGB in an image, 3 cross length cross breadth. We cannot do that. First, we need to permute the image into 1 cross 2 cross 0, and then we sort of want to use that. So this is it. Yeah. So then coming the concatenation is like appending two tensor together. You can do it in the row wise or column wise. Yep, that is done. Next operation is conversion to other Python objects. Yeah, I mean, you can convert your tensor to other types as well. Like you can the way we the way we converted list to tensor and PyTorch to tensor, the vice versa can be done as well. convert a size 1 tensor to a Python scalar so that we can have. Okay, this is not that important. Then GPU is here. How to access GPU? The thing is that every tensor holds two value: the gradient value and the device value. On which device the tensor is on. If it is on GPU, it will be very much convenient to use the GPU underlying GPU for the computation. So yeah, so the one way to check is that just to print x dot device, and to check if the machine has a GPU or not. A common way to say is that torch.qdot is available. If it is yes, then it is available. Since we turned on the GPU T4 here, we can consider it is available. We can set the device like this. We'll set the device to QDA if the torch.qdot is available is for true, otherwise it is CPU. And one more thing, recently M1 chip aligned computers are in the market, or laptops also are in the market. So we have another device option in the PyTorch as well. The accelerator is called MPS. So it is not currently added to the this is added to the PyTorch, but since it is a very old notebook, I guess not very old, like I would say 2-3 years is old. So I don't think that will be supporting this MPS accelerator, but it is there and it is released recently in 2023. It is just so how to convert a tensor normal tensor to a GPU tensor is that just write two and in the bracket the device name. This the set device function will give it a device like CPU or GPU. That can be set to sent to Y. GPU is enabled in this notebook. Yeah. And this is moving to CPU and moving to GPU just by typing dot two, and we're going to the CPU, and or you can use x.cpu as well, and similarly x.cuda as well, or x.2 the device name. This ends our first notebook on uh, the PyTorch tensor. Let us look at what's there in the second notebook. Hope something interesting. So we'll discuss this quite a bit later. Let's take a 5-10 minutes break and then we'll come back and continue for more 45 minutes. Yep.
Okay.
Yeah. Yep. So let's start discussing about the lecture slide number 2. The corresponding notebooks. So uh, in the slide number 2, we will see that how do we write a neural network code corresponding corresponding neural network code to uh, create a neural network in PyTorch. So if you're not familiar with that, we'll discuss that, and if you're familiar, you can skip it. And it starts by importing all these libraries and preparing the dataset. So this is a manual dataset that is created by the professor for this course itself, and uh, we are. I think this has notebooks with itself. Well, it shouldn't throw any error with me. Okay. And session. And to close this session. Yeah. Close. Let me connect this and try to run that. Yeah. So we'll start with the imports, and we'll then go to preparing the dataset. I hope it is, yeah, it is downloaded. So it is from the GitHub. So if you see, this dataset is of the size 100, and so it's just two-dimensional data, and just 100 cross 2, and y vector is just numbers of 100, and the class levels is 50-50, like 50% of the class the data belongs to class number 1, and 50% belongs to class number 2. Okay, so with that, this is the standard deviation. So since it is normal distributed, the mean and the standard deviation are the same, and this is a code to sort of scatter plot this data. So we have xtrain and we have xtest, and we just filter where this white train is 0 and where this white train is 1, and we filter that, and we plotted a scatter plot using this data, and we see that class 0 and class 1 has a clear distance boundary, and also they are equal in size. So this is the way to plot the this distribution, and the show function sort of gives us this chart as an output. So here it is. So this is a training set, and now we are looking at the test set. Similarly, the 50-50% distribution. So yeah, so now we'll start with coding the perceptron with NumPy, and then we will favor a path through this to code the same thing in PyTorch. Give 2 seconds. Yeah. So coming to the class perceptron. So perceptron, as we know, like it's a neural network that is fully connected, and that each of the input from the first layer is connected to the next layer. So what we do is that, so now we're here defining this class perceptron on NumPy, and we sort of defined the uh, weights and initialized it with zeros, and similarly the bias. Since the network has the input which has two features, and the output is one, I guess we can just design a very simple neural network. There will have two input layers and just one output layer. So this is the way. So we will have the number of features, and the weights is just uh, 2 cross 1, which is number of features cross 1, and the bias is just 1. And the forward function defines how all the inputs from the all the inputs will be propagated to the output layer. So it's just taking the input and multiplying it, getting a dot product with the weights and adding the bias. It's just wx plus p, and then we're sort of deciding the predictions, where if the predictions value is uh, more than certain threshold, we can say this is class 1 or the class 0. And similarly, doing the backward propagation, so we just sort of get the predictions and get the errors, and back propagate those errors to calculate, so update our weights and biases. So here we're just returning the errors, and if you see the training step, we're getting these errors, and we're sort of doing this gradient descent step here, where we're sort of updating the weights and biases to get the new weights and biases. And in the evaluate step, we we evaluate our model using the test data and test levels. So this is basically all the functionality that you need for a perceptron that is designed inside this class, and we can use this class for designing neural network and doing all sort of classification or regression tasks. Yeah. So training the perceptron, so we're just calling these functions. We made a perceptron object, and we sort of call the train function. The train function should train this model. Yeah, so since this is just a one layer model with just two inputs and 100 data set, this model is now trained completely, and the model parameters after the training is 1.227 and 1.34 the weights, and minus 1.0 is the bias. You can see we started with the 0, so this np dot zeros sort of create zeros in this step, the step that is provided. So we started with 0, and we sort of paved our way through the optimal to the optimal weights, which is 1.27 and 1.34. Evaluating the model, we evaluate the model with a test set, and we can see that the accuracy is pretty good, is 100%. Maybe because the data is not that big, and also it is very simple. And testing the testing accuracy, so it is training accuracy and it is testing accuracy. Testing accuracy is 93%, which is not bad at all. And deciding the distance boundary. So how do we decide the distance boundary? So here, like, what we can do is that we can sort of look into the weights and bias, and sort of uh, like create the point where, so sort of find the weights and find the biases from which there is a change in the prediction value, and we can join all those points to get a line, and that will be a descent boundary. There is a descent boundary learned by the uh, perceptron, which is 2D. So we did that. We plotted the descent boundary, and we can see uh, they give a clear separation between the training data set, while a little bit of error in the testing data set, but still it is fine. The line should be going through this like this, but still it is fine. We can see that using perceptron, by training the perceptron using NumPy, we get a pretty decent line, decent boundary. Yeah, and here we'll be doing the same thing with PyTorch. So it's very, uh, yeah, I guess they haven't. Yeah, no. In this code doesn't include the PyTorch NN library. I guess it's just the same thing but with torch. So here you see, here if you see in the perceptron, it is np dot zeros. Now it will just torch dot zeros, yeah, torch dot zeros. So it's just doing the same thing in the torch. I was hoping that they do call the NN library to create the neural network, but no. So they just did it with the raw PyTorch weights and biases. So yeah, so this is Perceptron Torch, and they have created the weights and biases using torch zeros, and everything is created into torch. Like the matrix multiplication is now in the torch method, and the square is also from coming from the torch, not from the NumPy, and everything else. So, but so if you look into this part, however, so we are sort of returning the errors here. But if you see in the NumPy part, we were designing this backward function by ourselves. I guess we do the same thing here as well. Yeah, we do the same thing as here as well. We do not use PyTorch, the neural network functionality, to do this. So we'll maybe see it in the next lecture. Sorry, not next notebooks, where the PyTorch 2 potential is used, but here it just copy paste from the NumPy part, and I can just run it directly. I guess it just NP is changed into torch. Yep. So these weights and biases are learned very similar to the prior method that we saw in the NumPy, and the test accuracy is also similar, like 93.33. We can see the distance boundary corresponding to this. Yeah, it's almost the same as the NumPy, because we started with 0 as well here, and given that given the same data set and given the same starting point, they're likely to learn the same thing, given that we do not change in the training paradigm uh, by anything. So let me kill this. Yeah. So let me open the next notebook. I guess lecture 3 notebook. This might have uh, code that is written, yeah, using PyTorch in an NN functionality. Let me connect. Yeah, connected. So this is just the normal imports that we are doing, and this is like from torch import NN. So NN is a tool that is specifically designed for neural network, and torch is a more generic library with tensors and operations and plotting to some extent and all these things. But this NN is solely designed to create layers, loss functions, optimizers inside the torch library, and so yeah, so we'll be using that, and it will be pretty much convenient to use NN other than directly uh, uh, creating the matrix and multiplying them and just backpropagating them. This is the helper function to plot. Yeah. Then coming to the gradient descent algorithm. So yeah, so just describing gradient descent algorithm. So I'll not describe it again because we have done this earlier, so in the lecture as well. So So what it is saying is that suppose if you have a z that is a function of two variables x and y. So here it is. Z is a sine of x square plus y square, and so what you want to do is that if we want the derivative of z with respect to x and derivative of y with z with respect to y, we need to write it manually. That is 2 into x into y into np 2 into x into y into cos x square plus y square. So it's like taking the derivative of this function and then using chain rule, expanding the inside term, which will make the second term 0 and at x square as 2x. One,
Yeah, continue.
yeah. So we will make this as 0 and similarly for the dz by dy. The point is that uh, yeah, the point is that uh, so we're manually writing this down for each and every functions. But when you design something in the using PyTorch earlier in just torch tensors, what we had to do is that given a function, we need to write the corresponding we need to write the corresponding differentiation for the function as well. And the more we increase the network size, we need to write the more complicated uh, 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 backpropagation function as well. So this is the case before the invention of autograph. So when autograph came, it sort of created this computational graph internally in the background, and when you are done with your final function, you can just call the function backward, and it will calculate the entire gradients with it, and you don't have to worry about it. So we'll just see like how manually calculating this and plotting this looks. So this looks like this. So this sort of plots all the gradient vectors across x and y, and yeah, so it's just a nice plot like to see how the gradients are pointing, and the gradients always point in the direction of maximum change. So yeah, since it is a contour of circle, so it is maximum change across the direction of the radius. So it is pointing towards that. Yeah, so it's just a lot of write-up for the vanilla gradient descent code. Now, yeah, now the PyTorch AutoGuard came. So I'll just read like deep learning frameworks such as PyTorch, JAX, and TensorFlow come up with a very efficient and sophisticated set of algorithms commonly known as automatic differentiation, or we call it AutoGrad or AutoDiff. And AutoGrad is PyTorch automatic differentiation engine. So it sort of calculates the gradient automatically whenever you are designing a function. Like you are sort of creating this function z. So you say that z equal to np dot sine x square plus y square, return z. So this z will go as well as it will. So the z will be a output of this two x and y, is a function of x and y. So a computational graph will be built between x and y as variable in the background, and x will always store the gradient that is calculated through it. So it is easier for us to access it later when we want to get the gradient. Yeah. So everything starts with the yeah. So as I said, the PyTorch tracks all the instruction as we declare the variable and its operations as it build the graph when we call the backward pass. And uh, building computational graph in PyTorch to indicate certain tensor contain large number parameters. Yeah. So I mean, so let's say we are defining a network and we're defining any function. So neural network is a function. We're sort of defining any function. But if we so by default the required grad set is set to be true. That means any computation that I do with using that variable should preserve the should require the gradients and should keep them for the later use. But if we set the required gas to be false, it is the same as using NumPy for matrix computation, except for the GPU. So we should always put the gradient required grad to true when we are training, because in training we update the weights and all these things. But like in the testing part, we need to set the required grad to false for all the weights. And an easy way to set it up is to take the models to the eval mode. So yeah, so it's like a simple graph. So we have this W and B that we have set the required grad to be true, and in the forward we sort of created this x wx plus b sort of setting here, get the prediction, and this is the square loss we're doing. Yeah, so we did that, and we can get the initial weight, initial bias, and prediction for it. So this is normal as a normal tensor. This is similar to the way a normal tensor would behave. But coming back to the backward propagation part, let's say, yeah, why did they define this? Let me see. Implementing simple comparison graph, forward pass, L2 loss function, maybe. Okay, so we can skip that. So yeah, so in the backward propagation, let's say we have a variable C that is the addition of A and B. Okay, and so the gradient function uh, uh, that we can see in the that correspond to C is the add backward. So if we run this, yeah, you can see the gradient function that correspond to C is the add backward object, and it is stored in this pointer. What it is doing is that it is remembering that C is the addition of two numbers, and the two numbers are A and B. So, uh, so we can check our gradient function in our loss and the gradient and the prediction that we discussed earlier. If we run this, you can see that prediction is a gradient backward of 10h, and loss is a gradient backward of power 0, I guess. Yeah, so it was just a normal L0 loss. So, what is our network? Yeah, here. So we put 10h here, and for square loss, we just square loss is square loss, I guess. So we have this difference as, yeah. So we did that. Uh, Analytical gradients. Not sure, but this means, but yeah, detaching. Yeah. So whenever we are working with tensor, and so we should always require set the required graph to true whenever we're training. And let's say we have a tensor and we need to plot that. So the plotting library is matplotlib, and we're working with tensor. We got some values, we want to plot that. Matplotlib directly do not accept the tensor torch tensors. What we need to do is that we need to uh, pass it numpy tensors or array, Python native array. So to do that, one way is to detach the tensors, uh, torch tensors from its original pointer and give it to the numpy. So the one way to detach is that, so there are several things that need to be detached. Like, so detaching means detaching from the computational graph. So if you do not want something to be in the computational graph, you can detach that, and also you need to remove the device as GPU to work well in the plotting. So yeah, that is detaching. You can just call dot detach to do that. Okay, this concludes this notebook. Let me go till the point where I can find at least one code that is written entirely for entirely on PyTorch, and it contains a neural network. Okay, I'll close this as a hopefully this will contain. Yeah, this contain the neural network code. So I guess I'll run this code, and I guess this will be the last code that I will be discussing today. Yeah, let me connect. Yeah, connected. So we'll be importing all these things and helper function for plotting our code, our data, and we're setting the seed here. And this block doesn't have anything to do. Yeah, setting the device, seed and device and everything. Yeah. So coming to this part, PyTorch neural net model or NN dot model. So PyTorch neural net model provides all these things that includes like forward pass, backward pass, and how to define the forward pass and all these things. So whenever we're trying to create a neural network from scratch in the Python, what we can do is that we can use a PyTorch class to design it. And since many of the things are designed for us, the initialization technique, the some regulation techniques and all. So since these are initialized somewhere, what you can do is that we can always create a class as a subclass of n model, because everything is designed inside this n model. So uh, so let me see. Okay, so they are generating the sample data here. Your sample data that is generated random by sampling from a random distribution here. Yeah, this Gaussian distribution. And yeah, now we are defining a actual neural net in PyTorch. So you can see the white net that was defined a very wide 512 neural net with one hidden layer and another 10H activation function. So you can see the white net is the actual neural network that is developed in PyTorch, and you can see how beautifully we are defining. So what we're doing is that we're saying that we're defining a sequential layer. By saying sequential layer, I mean that all the inputs from the layer 1, layer I will go to the all the inputs to the layer I plus 1 that is fully connected. So if the layer I is like has 4 neurons, the layer I plus 1 has like 5 neurons, there will be a total of 5 plus 4, that is 20 connections in between. That is fully connected. To define that, we can always call n dot sequential and define our layers. The first is a linear layer, which consists of like number of cells in the number of cells in the it's like input number of dimensions, then TNH, and then our output. And forward is like just like just passing through these layers. So it's just self dot layers dot x. So you can see how simply we designed a neural network without defining the weights, without defining the biases and everything. All these things are taken care by this n dot module module, where it does all these things internally. So we are getting the seed here. So we need to define the loss function now. So the loss function is MAC loss, and also we need to define the optimizer as well. So it's pretty common to use MSE loss with default setting, and if it is a regression problem, it is very common to use NLL loss or the cross interval loss, and all these functionalities are integrated inside that. To be honest, yeah. So we defined all these things, the loss and optimizer. So what we need to do is that we need to reset all the gradients, because what happens is that when a variable is in a computational graph, if we use it later and run some block of it using variable, that variable will again store the gradient for that corresponding part. So what we need is that before start to training, we need to zero out all the gradients that is there. So that is zero grad function, which will zero out all the gradients that is there. Then we have so once we zero make it nullify the prior gradients, we can pass the inputs to the network to get the predictions. And after getting the predictions, we sort of calculate the loss, because we want to see how much did we miss. And after the loss is done, so now the time for backpropagation and updation of weights. So earlier, if you could recall, we used to write the backpropagation code individually for each and every function. But now it is not the case. After the invention of AutoGrad, now you can just call loss.backward. Looking at the loss, which is the final entity, it will look into the all those ancestor of all those variables that is used to, or like added, subtracted, multiplied to get this value. So this loss.backward will help in that progression everywhere, like till the end point, starting point. And so this optimizer.step is SDT optimizer.step. What this indicates is that to update the weights and biases. So it corresponds to back propagation, and this corresponds to updation of weights. So I'll run that one, and I can see the running ones. We have this loss of 0.67. Then we have a training loop. So training loop is just four things. One is like forward pass, loss, backward pass, take a step. That's it. Just four steps. And if we do that for all the epochs and keep the track of errors and everything, we can. Yeah, thank you. Good day. So I think I'll end now. Yeah. So we can say that we can train these models using that. Yeah. And once we train that, we can fit a nice curve around that, and we can see the training loss decreasing over time. So there is a plot corresponding to that. And yeah, I'll check this, like by 1847 epochs works for the best. Yeah, so this ends our discussion on creating a neural network using PyTorch's own NN.module class. So I guess there is no more interesting notebooks that is there. There must be there, but it will be a repetition of the same thing. So what I need to do is that, I'll just check what else is here. Yeah, the week 4, we have lecture number 5, that is gradient descent variant. So nothing much to see here, because it will just be calling different variants of gradient descent. Lecture number 6 is again gradient descent variant. Lecture 7. Okay, lecture 7 includes regularization, but it's a new topic, we'll not cover it. And lecture 8 is also, I guess, revolution. Yeah. Let's go to the lecture 9. That is improving the training of neural network. It's just hyperparameter optimization where we test around with different activation functions, layer size, hidden layer size, and everything. Going to the final lecture of the week of week 10. It's just a part 2 of that. So your task is to go through all these notebooks and see how they're sort of creating this neural network from scratch using PyTorch, and how they are sort of improving it with time by tweaking the parameters and hyperparameters, not the parameters, the hyperparameters in the network. So we'll stop now today. So it's been like 1.5 hours or something. So we'll stop now, stop the recording now, and we'll meet again in the next week to discuss about any topics or code or if you have any doubts regarding that. But till then, bye bye. Thank you for joining, and thanks for being patient. So I'll close the session now, and we'll see you in the next week. Bye.